So let's begin. So before that, is my screen visible and am I audible? Okay. All right. Okay. So for today, I wanted to discuss mainly three things. So which are some thermodynamics, in superconductor. Okay, and so we'll look into the critical behavior of entropy, and also how the heat capacity goes as we move towards the critical temperature. So some critical behavior. And the last thing that discussed today is some electrodynamics using so electrodynamics in superconductor. That means London's equations, solving London's equations. So we'll solve London's equation for three geometries. So one is like infinite, semi-infinite superconductor. So one is for a semi-infinite, not a semi. It's one for a slab superconductor and one for a cylindrical superconductor. So we'll see how the magnetic field is distributed inside this superconductor, and we'll also try to calculate how the current is distributed along the superconductor and what is the direction and all. Okay. So these are the main three things that I hope to cover today. So at any point, if you have any question, please feel free to ask. Okay. All right. Okay. So when you talk about thermodynamics in superconductor, so the main thing that we look into is Gibbs free energy. So Gibbs free energy G is equal to the internal potential U minus Ts minus H times M. Okay, so one is the magnetic field. So H is the magnetic field that you have applied from outside, and M is the magnetization that has been developed inside the system. Okay, so this is generally true for any magnetic system or any system in presence of magnetic field. Okay, so this is one of the thermodynamic equation that we will use, and the another one is du is equal to T ds plus H dm. Okay, so this internal energy has this entropic part which is always there for all the systems, and this is the additional term for this magnetization and external magnetic field, right? So you can relate to this, that this actually looks very similar to the expression like this. So if you have something like du is equal to TdS minus PdV, so like for a gaseous system you have pressure and volume, so that contributes to your internal energy. So here you have to just replace P with minus H and V with M, okay, to go to a magnetic kind of scenario. So this is our main two key ingredients that we will be using to describe all thermodynamics in superconductor. Okay, so I can actually calculate d of G, so differential of G. So it will be given by du minus T ds minus S dt, and similarly minus H dm minus M dH. Okay, so let's call this equation 1 and equation 2. So now we'll be using we'll be taking this du and we'll substitute in place of this. Okay, so then we'll get something like this: T ds plus H dm minus T ds minus S dt minus H dm minus M dH, right? So you can clearly see that some of the things will cancel. For example, TdS and minus TdS will cancel, and also this HDM and minus HDM will cancel, right? So at last we are actually left with this two terms, s times dt minus m dh. So this is our differential of the Gibbs free energy, right? Or yeah. So once you have achieved this result, so you can clearly see that the entropy is actually given by this partial differentiation of this G with respect to T when the H external magnetic field is assumed to be constant. And similarly you can, okay, so there is a minus, and similarly for M also you can see that it is obtained by del G del T when the temperature is fixed. Okay, so we'll be mostly using this to get some information about the entropy, right? So okay, so let's step back and let's first try to analyze this part. Okay, so in a superconductor, so you can say that there is no magnetic field inside the bulk, or I mean normally for superconductor
in magnetization it will be del G by del H.
Oh yeah, right, yeah, thanks for that. Right, so for superconductor what you can do is actually the magnetization is related to the external field. So normally normally there are two parts. So there is the internal magnetic field and the plasma magnetization. But for superconductor you can assume that inside the superconductor there is a magnetic field. So the magnetization and the external field is related by this simple equation. So m is equal to minus h by 4 pi. So here just to mention, so this is actually in CGS. So actually most of the old books are written in CGS units. So yeah, I am just following some of those. So that's just bear with me for now. So m is minus h by 4 pi, right? So I can use this expression and I can put it back inside here. Okay, so let's see what we get. dg is equal to s dt minus so m is again h by 4 pi and dh, right? So now we can actually integrate over this whole equation. So dg is equal to sum minus s dt plus integration h dh 4 pi. Okay, so basically what we can do is we can basically write this whole integration as this thing. So g in presence of magnetic field h is given by g without the magnetic field plus some h square by 8 pi, right? So all this entropic part, so because which is there for all cases, it is there for metal, it is there for any cases. So this entropy part is always there. So we are absorbing that entropy part into this G naught. So G naught is the Gibbs free energy without any magnetic field. Okay, so that is, so I am absorbing everything like SDT inside this G naught and some initial condition in times inside this G naught, right? So this is basically the how this G looks like in presence of a magnetic field H, right? So when you have obtained that, so this is something that we are doing for when the H is less than Hc. So Hc is a critical field. Okay, so critical field of superconductor. So that means if I apply Hc amount of field, then the superconductivity goes away. So similarly, we can actually find a similar expression for when we are exactly at the critical point. So we know at the critical point superconductivity has vanished, so gap, there is no more any gap if you talk about microscopics. But we can similarly find a this G for the normal metal. Okay, so G with a subscript n, so it is for a normal metal and it doesn't depend on the field anymore, right? Because initially the gap would be dependent on time, so that's how the time the gap would be dependent on temperature and this field, magnetic field. But normal metal doesn't depend on any of these things. Okay, so the Gibbs free energy G normal metal is again given in terms of G naught. G at 0, 0 magnetic field plus hc square by 8 pi. Okay, so here, because we are sitting exactly at the critical point, okay, so I am just plugging, instead of h I am plugging hc. Okay, and I am not writing any h dependence for the normal metal because that doesn't depend on any h. Okay, so nice, we have made some progress. So this is how the G looks like. And if we just take this difference of GH minus Gn, so that actually tells me that when I am going from or that tells me that what is the excess Gibbs free energy when I am in a superconductor, right? So that is, I mean, that is something that you can calculate. So what we want to calculate is we want to calculate, as I mentioned before, the entropy's expression. So entropy is given by minus of del G del T in a fixed field. Okay, so let's try to calculate how this looks like. So for example, S of n, so S of n is actually entropy in the normal metallic state. So S of n, or let's say minus S of n, will be given by del Gn and del T with the fixed field. Okay, so anyway, so the field is already fixed. So because I have put Hc here, so I can directly calculate it. So let's say there will be some del G or yeah, so del G naught will be, let's say, not there because it is some constant thing. It doesn't depend on temperature. Okay, or I mean, it doesn't actually matter. I mean, you can keep that, but what we are interested in, we would like to really keep this critical field part. So that is just, you take derivative with that. So Hc del Hc del T by 4 pi. Okay, so there can be some constant, and but we don't really care about that. So this is the entropy in the normal state. Okay, similarly we can calculate the entropy in the superconducting phase. All right, so so in the superconducting phase, I'll again take this G of H, and I'll just take a derivative with respect to this temperature at a fixed H. So if I have a fixed H, so then actually this automatically drops down. Okay, because I'm fixing H, and that means that this will not also change as a function of temperature, or this is anyway external field that I am applying, so it need not to change with the temperature, right? So here so it is just some constant. Okay, so in these both equations, the constants are actually same. Okay, which is coming from terms which is not dependent on the field. So if you calculate this, for example, if you just calculate so you have a question, Lava? So you can just unmute and ask. Okay, anyway, so at any point if you have any question, just feel free to ask. Okay, okay, so the thing that we are interested in, we are going to calculate the entropy difference between normal and superconducting phase. So Labha, do you have any question? You are raising hand. Okay, anyway, so so this is clearly given by minus Hc by 4 pi and del Hc del T. Okay, something like that. So and so experimentally what is observed is that this del Hc del T is actually negative. Okay, so you can see that, so if this thing is negative, then the right hand side is actually greater than 0. So that means Sn minus Ss is greater than 0, which implies that in the normal phase, or in the metallic phase, the entropy is actually larger than the entropy of the superconductor. Okay, just a very simple kind of analysis tells us that this entropy is actually larger for normal. So one way to physically see this is that in a normal metal, so there is no order. So but in the superconductor there are some Cooper pairs, right? So in some sense there is less amount of disorder in the superconducting phase. So that's why we can physically motivate that probably this makes sense. In the normal phase the entropy is larger. Okay, well, so with that now we can actually calculate some other different this thermodynamic quantities. For example, we can look into how does the heat capacity looks like. So normally just a little prologue before I just jump into that heat capacity. So normally the heat capacity is given by something like this. So C V is given by some, let's say, alpha T plus beta T cube. Okay, so this alpha T is the electronic contribution, and this T cube is contribution coming from phonons. Okay, so for a normal metallic system you will expect this is the case. So for when the T is actually much smaller, or let's say T is much smaller than 1, or let's say some alpha T is much smaller than 1, so then it is mostly this linear behavior, and for larger temperature you will get this cubic kind of behavior. Okay, so normally if we just think about very small temperature, you would expect that the CV will be just a line, just a straight line with respect to T. Okay, and that is the case for all of the metals, but in superconductors what we see that, so say experimentally what we observe that, so there is this TC. Okay, and below TC the behavior is actually something very bizarre. So it actually grows somewhat exponentially up to TC, and then it suddenly drops to the this straight line, and then follows the normal metallic path. Okay, so this kind of CV is actually signature for there is some superconductivity, right? So we will try to argue that how does this this kind of temperature behavior with temperature actually appears for a superconductor. Okay, so from the perspective of thermodynamics, the CV, or just let's say his heat capacity by T, is given by del S or del T, or let me just take it right, del S dt ds dt, right? So we already know how does this this whole entropy difference behaves. So all the temperature dependence, everything is within this HC. So what we will do is we will just take that expression and we will just do a dt over this whole left hand side and right hand side. So now we can do d dt of S normal minus S superconductor, so which will be given by, so there are two terms on the right hand side, so I'll do a product rule. So the first term, let's say, is so HC by 4 pi, let's say d2 HC dt2, and then on top of that we have this another term 4 pi dhc dt whole square. Okay, and with that we will just multiply the T, okay, to get the heat capacity. So this is so the left hand side is the difference of heat capacity of normal phase minus heat capacity of superconducting phase. Okay, and this actually gives us this thing, or let's say we write it as the other way so that we don't have to carry the minus. So Hc by 4 pi 2Hc dt2 plus 1 by 4 pi c dt whole square and times t. Okay, so I mean this might look a little bit complicated, but this will actually be simplified significantly. So okay, so for example, so you can see that below Tc, so when T is less than Tc, so then what happens is the right hand side is actually a positive quantity. Okay, so the temperature dependence I will introduce slowly, but so let's look at this particular limit when this T is exactly at Tc. So when you are sitting exactly at Tc, so the superconductivity has vanished, and as a result, so you need actually zero field to break superconductivity because it is already broken. So Hc is 0 at T is equal to Tc. So at exactly that point, so I can write this delta C, Cs minus Cn as Tc. So the first term will actually it will vanish because of this Hc. So then it is 0 plus 1 by 4 pi and dhc then dt. So this is just Tc by 4 pi and dhc over dt whole square. Okay, so this is the difference of heat capacity between the normal and superconducting phase. Okay, so any question? All right, so actually we will now let's try to so the Hc, so this is called the critical behavior of this critical field. So Hc near this transition is given by H0 times 1 minus T by Tc whole square, right? So this is, I think you have already you have been asked to prove this probably in one of the assignments. So let me start with this. So the H critical is given by 1 minus T by Tc square. Okay, so at near any critical point, you will see that the functions only appear as some function of T by Tc. Okay, so this is always the case if you are near a gap closing point or near a transition. So this is a like trademark of a phase transition. Okay, or this is also called a critical behavior. So the H is given. Okay, now you see that what we have done until now, that we have expressed this change in heat capacity in terms of H and derivatives of H, and also we have expressed the this entropy difference in terms of H and derivatives of H, right? So we can take this Hc and we can try to plug into this San and we can see what do we come up with, right? All right, so let me take this. So let's calculate this del Hc del T first. So del Hc del T will give us H0. So 2H0 T by Tc square and minus, right? So yeah, so I'm actually mixing this del and del T, but because we are assuming that H C only depends on t for now. So this del t and d dt are same. So I am not being very much careful about it. Okay, so del h c del t is something like that, and then I can write the full t dependence. So 1 by 4 pi, so it becomes plus 2 h naught square 1 by tc square t by tc square, and then I have this hc, which is given by 1 minus t by tc whole square. So let me simplify this a little bit, and then we can look at this expression. It will be cube, yeah. So this is the entropy's difference and how it changes as a function of t. Okay, so you can see that at t is equal to tc, it vanishes. So t equal to tc, I mean this becomes 1 and this becomes 1, so this whole thing vanishes. So the normal phases entropy and the superconductor's entropy becomes same, and afterwards it stays same. Okay, so this is an important result. Okay, and the other thing is, so we want to calculate cs minus cn minus cn. Okay, so which will be given by d of dt t times dt of sn minus ss, right? So we can just take the derivative. So t times h naught square by 2 pi tc, and the derivative from the first term will give us 1 by tc, and the derivative from the second term will give us 3 by t square by tc cube. Okay, and we see that there is additional t, so which we will pull inside of the square bracket. So then it becomes h naught square 2 pi tc t by tc minus 3 t square by t t cube by, or let me write it as t by tc whole cube. Okay, yeah, so I think I have messed up a sign here. So is this, oh yeah, I have messed up a sign, so I'll just add this minus. Okay, so here you can see something astonishing, that so there are, so in the heat capacity, so there are like there are like two kind of terms. So one is linear in t, so one is some linear in t, and another one is some t cube. Okay, so it actually tells you. So by the way, so we are not actually taking account of any phonon, so this t cube is not because of phonon. So this t cube is appearing just because we have this superconductivity below the tc. Okay, so if you just want to look into this its individual heat capacity, so which will look something like this. Cs will be something like t by tc whole cube. Okay, so because we are looking just at the difference, so you can just, so let me write it a little bit properly so that it becomes absolutely clear. So I have 3 t by tc whole square minus t by tc. So the difference of cs minus cn has these two powers. This is square, yeah, this is cube, and so this is two powers of this cubic and linear order. Okay, my screen has stuck, I see. Okay, so let me, yeah, it's fine now. Yeah, okay. Yeah. So so now we can see that this difference, you can take the difference, and the difference has these two terms which you can take separately and you can make some sense of those. So let's say CS is given by h naught square by 2 pi tc times this 3t by tc whole cube. Okay, and the normal in the normal metallic phase, the heat capacity is given by h naught square by 2 pi tc times just t by tc, right? So let me try to draw this in a plot. So for example, if we try to draw this thing, so temperature versus the heat capacity, right? So for a normal metallic phase, so as I showed you before, so it is just like a straight line. Okay, and let's say this is our tc. So we see that below tc, so there is actually a t cube behavior in the superconductivity in this heat capacity. So it will actually grow as something like this, and it will pick up. And as soon as it hits tc, so superconductivity is gone, and then it will just directly be this linear behavior. Okay, so this is how you can understand the this CV of or the heat capacity of this superconductor, right? So you see that below the TC, so the CV is actually even smaller than the normal case, and as soon as you reach the TC, the phase transition point, it actually it peaks up and then it follows a normal metallic path, right? So physically, how do you understand that? So physically, so one way of interpreting this is, so when you are much deeper in this superconducting region, so you have a large gap, right? So large gap means, so if you try to increase the temperature, so then you cannot cause any thermal excitations because there is a gap in the spectrum, right? So because you cannot cause any thermal excitations, so then it is smaller. Okay, so but as you increase the temperature, you will see that, you know already that in finite temperature the gap actually has some form of like this. So the gap, so delta as a function of temperature, so gap actually decreases to this Tc, right? So as you increase the temperature, the gap decreases, and as a result, for that particular temperature, you can actually excite more and more particles thermally, right? So as a result, you see that there is this kind of peak. Okay, and beyond that, so it becomes a normal metal, so it follows the normal metallic path. Okay, so yeah, so any question? Okay, okay, so okay, so let's look at some of this London electrodynamics. I think my connection is very poor today. My screen got stuck, so let me join again. Okay, it's back, I guess. Okay, so let's look at this London theory. So you have already studied the London electrodynamics, so let me just recap that part very quickly. So in London's theory, so what he does is, so he assumes the superconductor as a two fluid model. So that means, so two fluid model is given by some superfluid density plus some normal fluid density, and then so both of these add up to the total particle density. Okay, on average the particle density. Okay, if you add this up, and both of these contribute to current, right? So if you look at the current, so current will be given by this minus charge times the, so let's say the superconducting density times the velocity of the superconducting particles, and plus this normal particle density and normal particles velocity, right? So this part you will call as the supercurrent, and this part you will call as the normal current, right? So in the normal for the normal current, so that obeys the Ohm's law that you already know. So let me distinguish them first, Js plus Jn. Okay, so the superconducting in the normal part, so the Jn, so you already know what the Jn is. So Jn is given by sigma normal times the electric field. So whatever is the applied electric field, your current density will be in proportion to that. Okay, and the proportionality constant will be given by conductivity sigma n. So my screen is actually
screen got stuck.
Yeah, my screen is freezing. So let me actually really join again. Okay, I hope this will work now. Okay, so as I mentioned that, so the normal current is given by the Ohm's law. So this is like a linear response, right? So if you apply some small electric field, then your current actually depends linearly to that electric field, and with that proportionality constant, which is called the conductivity. Okay, so but for the supercurrent it is not that simple. So for the supercurrent, so you will have to do some little more. So in your lectures you have already that's a professor actually already showed you some way, so I'll show you a different way how to get the London's equation. Okay, London's equation of electrodynamics. So this is okay, so let me first write some Newton's law kind of thing. So m dvs, so dt, so this is a fully semi-classical, so no microscopics in this. So if we have just electric field, right, so then this change in momentum is given by the applied the force because of the electric field. Okay, and because the charge we are concerned here is the electron charge, so that's why this is a minus E. Okay, so this is simple. So so this is for only electric field. Okay, so you introduce magnetic field soon. Okay, so so the dvs dt is given by minus E by m. Okay, and with the v, if we just multiply these additional constants like E and ns, then we will be able to make this supercurrent, right? So let's just do that. So let's multiply minus E times ns with this v vs. So these are constant, so it will just directly go through the derivative, and the right hand side also will just do the same, E square ns by m. So this is your current, this is the supercurrent, and E square ns by m E. Okay, so now this actually fully describes your electrodynamics in presence of single just this electric field. Okay, so this is simple, but we want to do a little more. So on top of the electric field, we will also like to add the magnetic field, right? So then similarly, I will again start with this this Newton's equation. So dvs dt is given by minus E times E plus the Lorentz force. Okay, So we see that the left hand side and right hand side both has the Vs. So solving this is not that easy anymore. Okay, so let me just take this m and divided it on the right hand side. Okay, so we can do some manipulations to this expression. Okay, so for example, I can write the left hand side, so because this is a total derivative, right? So I can write in terms of a partial derivative, so something like this. So del Vs del t plus Vs dot grad acting on Vs. Okay, so I'll just keep the right hand side as it is. So E plus 1 by C. So all of these things are time dependent and all. Okay, I'm not being very much careful to write those arguments. So time dependent and space dependent, right? Vs cross B. Okay, so now so you might remember some identity from your vector calculus. So for example, so this is the important identity that we'll use. So let me write here. So if we have half grad of any a dot a, so that means some a mod squares grad, then this actually gives us a dot grad times a acting on a plus a cross curl of a. Okay, so we can actually substitute this. I mean, we can use this formula and we can just substitute this with the rest of the terms. Okay, so that is what I am going to do now. So this will be half grad a, let's write it as a mod square minus, okay, so this was not a, this was just my Vs, minus Vs vector grad of Vs, right? So and the right hand side is same. All right, so now we can do something. So we can actually take a gradient or take a curl of the whole expression. Okay, so that will simplify our life a little bit. Okay, so before that, let me do some arrangements, quick arrangements. Plus E by M vector electric field E is equal to Vs cross grad of curl of Vs plus B by E B by MC. Yeah, so that's fine. So now take curl of both sides. So I'll get something like del t of, so curl and this del t commutes, so I'll just plug that in, plug that through this time derivative Vs. Okay, and so we notice that so curl of some gradient is actually 0. So for the second term we will actually directly put 0 here, and then we will have E by M curl cross E. Okay, so we'll use Maxwell's equation to reduce this in terms of magnetic field, but before that we will have additionally curl of Vs cross curl cross Vs plus EB times MC. Okay, so here so let me use this Maxwell's equation, which is so curl of E, as you know, is given by 1 by C del B del T. Okay, so I'll just plug that in here. E by MC plus del B del T. So we see that del T actually appears in front of both of these terms. So I'll just take out the del T, and in the parenthesis or in the square bracket I'll write as curl cross Vs plus so am I missing something? Okay, so it should be actually, no, seems fine. Okay, probably I'm missing this, so there should be a minus, probably this should be a minus. Yeah, I'm missing some minuses, but anyway, so let me E by MC del B del T. Oh, not del T anymore, so B. Okay, and then I will have on the right hand side also grad cross Vs cross grad of Vs. So there should be also some minus. I have made some mistake probably. So EB by MC. Okay, so we see that in both of the right hand and left hand side, so this term is actually same. Okay, so and also what happens is that in steady state solution, or let's say in equilibrium, so in equilibrium means that I have turned on an electric and magnetic field, and I have waited long enough so that there is some transient behavior which has diminished, and then I am looking into the system. Okay, so that is what the equilibrium is. So in equilibrium, so this is actually 0. So grad of curl of Vs is given by E by MC times B. Okay, so okay, so if that is the case, then actually so this equation is satisfied. Okay, and this is a simple assumption. In equilibrium, this is what happens. Okay, and I can now plug in this with this Vs. I can now multiply this the elementary charge minus E and the density of the super fluid, okay, which is Ns. So then it becomes a current. So cross minus E Ns Vs, and also on the right hand side I will do the same, minus E square Ns MC and B. Okay, so the left hand side becomes a current, curl of current Js minus E square Ns by MC. Okay, so this is one London's equation. Okay, and so from this you can actually get the other expression. So which is, so first of all we have to use the Maxwell's equation. Curl of B is given by mu 0 j. Okay, and there is addition 1 by C square del E del T, but we assume that this is actually 0 in equilibrium. Okay, so it doesn't have a explicit time dependence, so that is 0. Okay, and so I already know what the B looks like, right? So something, so I can just invert this equation to find what the B is. So I will directly write it as grad cross J if you may. Okay, what I have done here. Okay, so let me actually first do this. Curl B is mu 0 curl of J, right? And yeah, so on the right hand side I will now plug in this thing. Okay, so on the right hand side I'll directly write mu 0, so there is a minus E square ns and mc. And from your vector calculus you already know that, so if there is a curl of some vector field B, so which will be given by gradient of divergence of B and minus Laplacian of B. Okay, so for a magnetic field from the Maxwell's equation, you know that this part is already 0, so then you are left with minus grad square B. Okay, so just to write it in a tidy way, so I'll just cancel the minus. Mu 0 E square ns mcb. Okay, so this factor in front of E is actually called as 1 by lambda L square. So lambda L is a London's penetration length. Okay, so square B is 1 by lambda L square times B. Okay, so this is London's equation 2. Okay, so this lambda L is written given in terms of this mc mu 0 E square ns square root. Okay, so you see that this is, I mean, if you have mu naught, so then that means it is in SI. So yeah, this is written in SI. Okay, but if you don't have this, if you want to convert it into CGS, then you just plug in, instead of mu 0 you plug in 1 by 4 pi, so then you will get the penetration Landau's screening length lambda L. Okay, all right, so that's good. Yeah, so there is one important question. So like as you have seen before, that how does this temperature dependence, I mean near the TC dependence happens for all of this entropy and also the this heat capacity, right? So we can try to do similar analysis for this screening length as well. Okay, so what does this lambda L tells me? So lambda L tells me that crudely, if I have some superconductor, okay, so this is some superconductor, and if I apply a magnetic field, so let me draw it in different colors. If I apply a magnetic field, so as soon as the magnetic field again my screen got stuck. Okay, let me rejoin again. Okay, yeah, so what so I was telling about, so what happens, so what is the effect of this kind of a magnetic field dependence, right? So that means that if I have some superconductor, okay, and if I apply an electric magnetic field, let's say, then as soon as the magnetic field enters this superconductor, then it is screened exponentially, then it diminishes and becomes 0 or becomes very small over a length of lambda L. Okay, so that is what this means. So so in this theory, so this theory was actually motivated by some previous theory, which is now named as Gotter and Casimir model. So they actually introduced this two fluid model. So there they approximated, so they calculated that this superconducting density or ns is it behaves approximately as 1 by 1 minus t by tc to the power 4. Okay. Okay, so now, so if my ns depends on t like this, so I can plug into this this expression of lambda l, and I'll be able to do some I'll be able to conclude something about this lambda l, right? I mean, how does it depend on temperature? So then the lambda l will be mc mu naught e square, okay, divided by n. So n is the total particle density times 1 minus t by tc to the power 4, and there is a square root. Okay, so what does this tell us? So this tell us as t reaches tc, okay, then the 1 minus t by tc to the power 4 becomes 0, right? And then lambda l is actually infinity. So that means that, so at tc, as the superconductivity vanishes and the system becomes normal metallic, then there is no screening. So the magnetic field actually retains its full amplitude, and it just propagates through the metal. Okay, so then it becomes like transparent. Okay, so I mean, just on a related note, so we see that when we are in the superconducting phase, we see that the superconductor actually how should I put it? So the superconducting actually repels the magnetic field, right? So, but if we think about conductors, the conductor actually is kind of transparent to the magnetic field, but the conductor again repels or it screens the electric field, right? So I mean, this is two main differences between a conductor and superconductor, okay, from the perspective of the electromagnetic fields. Okay, so nice. Okay, any question? Okay, so if not, so let's try to, so this is, so this London's equation you already know, so that should be okay. So what I want to do is, now I want to, depending on this London's equation, I want to solve some electromagnetic problem. Okay, so let's try to see few of those. Okay, so I have a semi-infinite superconductor. So you can think of this as in the following way. For example, let's say so this is my y direction, okay, and the semi-infinite superconductor is given in the region for y greater than 0. So that means this whole region. So this is my superconductor, okay, and rest of the part is like vacuum, you can say. Okay, it's vacuum, and so this direction is actually your x-axis. Okay, so I am using a right-handed coordinate system. So this is x, y, and z is coming outward of the page. Okay, so z is outward. So this is how the so the superconductor is oriented. Okay, and what I am doing is, so I am applying a magnetic field. So let's call it B applied. So I am applying a very simple magnetic field which has a constant amplitude, so B naught, and so it is in the z direction. Okay, and it has some oscillatory phase part, time dependent phase part, so which I will be writing as e to the power I omega t, real part of e to the power I omega t. Okay, so this is the applied magnetic field. Okay, so now, so the question that I am asking is the following. So what is the magnetic field inside the superconductor? So and if there is magnetic field, so Maxwell's rules tells us that there is should be current. So what is the supercurrent because of that? So you know that already the very much inside the bulk, so the superconductivity, the magnetic field becomes 0. Okay, so the question we are asking is how does it go to 0 exactly? Okay, so probably this is something that you have done, but let's try to formulate this very systematically. So our main equation for this problem will be this London's second equation, so which tells us the Laplacian of B, vector field B, is given by 1 by lambda L square. So lambda L is the London screening length times B. Okay, so yes, okay, so now I want to solve this equation, right? So now before trying to trying to solve this full partial differential equation, we'll try to do some simplification by some arguments, okay, or by some symmetries. Okay, so here we see that so the magnetic field is applied in z direction. So whatever is the magnetic field which gets induced inside the superconductor should also be in the z direction. Okay, so first of all, so let me write it as that. So magnetic field should be in the z direction. Okay, and we see that so z is so the sample is infinite in the z direction, and it is also infinite in the x direction. So we are asking the question, how does it decay inside this I mean on the y axis. So y in the y direction, it has one of the surface. Okay, so it makes natural sense to ask for a function which actually depends on y, okay, and doesn't depend on any other two of these two spatial dependencies, x and z, because those directions are infinite. Okay, and typically when these are infinite, so then the solutions don't depend on those particular directions. So it will only depend on directions which is finite, I mean which has a edge or surface or something like that. Okay, and the other assumption is that we're not looking at transient behavior, we are looking at some steady state kind of solution, so it also, the solution would also carry this phase e to the power I omega t. Okay, so basically I am looking for a solution of this form. Okay, so you see that by argument we have actually reduced a lot of complexity. So then that means that this differential equation is now simplified, and the PD, the partial differential equation, now becomes a ordinary differential equation of a single variable y. Okay, so so I'll just keep this thing, so del, or let's say d2 dy2. Okay, so I'll bring the 1 by lambda square on this left hand side, and this will act on b of y. Okay, and there can be e to the power I omega t, all of those things, but which is not important. So that will be, so we'll plug that e to the power I omega t and z hat at the end. Okay, so yeah, so this is the full differential equation that we have to solve. Okay, so and so this kind of differential equation has a solution like this. So b of y can be written in terms of c e to the power some minus x by lambda L. Okay, and plus some d e to the power minus x by lambda L, plus x by lambda L. Okay, so these are like two kind of solution. One tells me that as we go across this y, one of the solution will decrease exponentially. Okay, my internet is bugging me today a lot. Okay, all right, yeah. So the general solution that I have written at the bottom, that tells me that the solution has two parts. One tells me that the magnetic field will decrease exponentially into the bulk. Okay, and the other solution tells me that the magnetic field will increase exponentially into the bulk. Okay, so from this physical argument we see that the second solution that just cannot happen, right? So because magnetic field normally in any superconductor doesn't increase, it only decreases. So from physical point of view, we will set this to be 0. Okay, we will set d to be 0. Okay, so then the solution has only this C part. Okay, so B is given by only, okay, so not X, it is Y. Yeah, by is given by C e to the power minus y by lambda L. Okay, so now I have to find what is the value of this C, okay, which is this constant. So I know that outside this superconductor the magnetic field is constant because I have applied it from outside. Okay, so which is my choice, I have chosen it to be constant. So B at 0 is given by the this B naught. Okay, so B at 0 is given by the B naught. Okay, and if you plug it in the solution like this, so you see that you directly get C e to the power minus 0 by lambda L. Okay, so this becomes 1, so which tells you that the constant C is just B naught. Okay, so this solution you already are aware of. So this tells you that the By is just an exponentially decaying function minus y by lambda L. Okay, so let me write the full solution. So the vector B as a function of r and t will be given by the direction z hat in the z direction, and then we'll have this B naught e to the power minus y by lambda L, and also this oscillatory part given by real part of e to the power I omega t. Okay, so this is something that you already know. So if you want to plot it, so like so then you see that at y is equal to 0, this was B naught, and it decays exponentially in a length scale of lambda L. Okay, so this is all good, but what we want to do, we want to do a bit further from this. So we want to calculate what is the current. Okay, so we already know that B should be in the z direction. Okay, and now we are asking, okay, what is the current? So we'll take help of the Maxwell's equation, so which tells us curl of B is given by mu 0 j. Okay, so I already know B, so I can easily calculate the curl. So let's calculate the curl. And I have only one of the component, so which is in the, which will be sitting in the this k part or the z direction. So it will become B naught e to the power minus y by lambda L. Okay, so you can see that so what is okay, so I hat, in the I hat direction, so I'll have some del y acting on e to the power minus y by lambda L. Okay, and then I will have everything, so all of the other part will be 0. Okay, because it only depends on y. Okay, and all of the rest of the derivatives are I mean x and z. Okay, so you'll see that all of the other terms are actually 0. So that tells us that it is I hat, so derivative will bring back 1 minus B naught lambda L and e to the power minus y by lambda L. Okay, so this is curl of B, which is equal to mu 0 j. So we see that this mu 0 j is also just y dependent, because that is also very natural. If the magnetic field in that is a function of y, then that can only give rise to a current which is also a function of y. Okay, so the j is given by minus I hat B0 lambda L mu 0. So let's try to visualize the current. Okay, so as I have shown you that this is y direction, this is x direction, and the superconductor is given in the y greater than 0. Okay, and my magnetic field is in the z direction. So this tells me that the current is flowing in the minus x direction. So for me the minus x direction will be in this way. Okay, so current flows in that particular direction, and as you will go inside the bulk, so it will exponentially decrease, and at some length lambda L it will just become 0. Okay, so that is how the current looks. It's like it is laminated, very laminated on the surface. Okay, all right. So yeah, so this gives some complete kind of picture of how does the magnetic field and the current actually looks like. Okay, so now we'll make this problem a little bit more complicated, and we will introduce another surface. Okay, and we'll see that how does the this thickness of a slab and this lambda L that plays a role. So there is a competition between these two length scales, so which will become very clear. So this is so now let's look at superconducting slab. Okay, so by that I mean that I have a superconductor, so which is actually between these two lines. So this is my y direction. Okay, and this is again my x direction. Okay, so this is given by some plus a and minus a. Okay, and in between this is a superconductor. The thickness is 2a. Okay, and this is when I mean in x direction also it is infinite, and in z direction also it is infinite. Okay, so we have just introduced a new surface for this case. Okay, so yeah, so that's it. So here also we'll do the exact same thing. So we'll start from the London's equation, and then we'll try to solve it, and we'll try to see how the current looks like on the surface. All right, so London's equation is given by grad square minus 1 by lambda L square acting on B. Okay, so here also the applied magnetic field is so this is given by something like this. So B applied. So like the last time, this is a constant magnetic field in the direction in the z direction, and it has an oscillatory part. Right, so yeah, and from this from again arguing that what should be the solution, what should be the form of solution, so we propose an ansatz, so which is like the B should be also in z direction. Okay, and because the x direction and z direction is infinite, so the solution should not actually depend on that those directions. Okay, so the solution should be only a function of y. Okay, and it has the same phase as the applied magnetic field. Right, so the logic actually goes the same way like for the like we have done in the last problem. So we'll plug in this ansatz in this London's equation. Okay, and so we'll get something like this. So we'll get d2 dy2 minus 1 by lambda L square acting on this B of y. Okay, so now you know that, so this kind of equation has solutions which looks like e to the power x by lambda and combination of e to the x minus lambda. Okay, but for this particular problem, so we can actually take the help of symmetry, and we can write this linear combination in terms of the sine and cosine. Okay, so because the problem now at hand has this even symmetry, right? So we can take we can take even or odd solutions of this kind of function. Okay, but you see that this e to the power x minus x, it is neither odd or neither even. Okay, so we'll like to just take linear combination of these, so which are just called cosine hyperbolic and sine hyperbolic, right? So sine hyperbolic x by lambda L and cosine hyperbolic x by lambda L. So you don't have to do that. You can start from this e to the power x by lambda minus lambda, and you will see that you will get the similar exactly thing. Okay, but by doing this, we'll actually reduce few steps. Okay. Okay, so actually the cosine hyperbolic solution that tells me that so inside the bulk I will have something like this, and as it goes outside it will just match the external magnetic field, okay, which is constant throughout. Okay, so this is something that cosine hyperbolic tells me. On the other hand, the sine hyperbolic tells me that when we will go across this superconductor, it will actually change sign. Something like not a very good thing. Yeah. So this is what sine hyperbolic tells me. So, but clearly, because this kind of a solution will never match our boundary condition. So our boundary condition is that outside this slab, the magnetic field is constant, it doesn't change sign. Okay, so this kind of solution is just ludicrous, right? So we should not actually choose this solution. On physical grounds, we are throwing this away. Okay, and we will be just keeping this cosine hyperbolic solution. Okay, so b of y will be given by c cosine hyperbolic x by lambda L. Okay, so now we'll have to match the boundary condition to find the coefficient c. Okay, so we have two boundary conditions. So one is b of a is actually b naught, and b of minus a is also b naught. Okay, so both of these will actually, you will see that this both of this will be satisfied, and also cosine is a even function, so that's why it is easier to use this thing. So b, it is given by b naught, and will be c cosine hyperbolic a by lambda L. Okay, so the c is just b naught cosine hyperbolic x by lambda L. Okay, so all right, so the solution, so we have now obtained the solution. So b of y, okay, so what I have done here, so this should be a, yeah. So b of y will be given by b naught times cosine hyperbolic y by lambda L divided by cosine hyperbolic a by lambda L. Okay, so this is the solution, right? So let me actually write the full solution with all of the vectors and all. So b vector is this with this oscillatory part given by e to the power I omega t, and it is also in z direction. Okay, so you see that when y is equal to a, so it just becomes b naught. Okay, that's because that's how we have chosen our this coefficient. Okay, so this is actually a good solution. Okay, so we'll understand this solution in detail, but before that, so let's see what is the current distribution in this slab. Okay, so similarly we'll calculate the current by calculating the curl. Okay, so let's write this out. And I have only the z component. So the z component is given by b naught cosine hyperbolic y by lambda L divided by cosine hyperbolic a by lambda L. So similarly like last time, so you see that we will have only I hat. Okay, so it is in the x direction, and so we'll have just this derivative, right? And then this will be then the other all of the other things will be 0. So let me directly write it as cosine hyperbolic a by lambda L, and there is this del y cosine hyperbolic y by lambda L. Okay, so derivative of a cosine hyperbolic is just a times sine hyperbolic x, right? So let's just use that. So there was also this b naught factor not, so it becomes sine y by lambda L divided by cosine h a by lambda L. Okay, and they divided by lambda L. So this is the form of the current. So let's first have an overview of this result. So as I told you before that, so let me draw here. So this is my slab, right? Okay, or let's say this is my y direction, and I want to plot the magnetic field inside this superconductor, right? So superconductor is given by minus a to a. Okay, and so the magnetic field looks something like this. So magnetic field comes here, and outside it is just constant, and in between it is actually given by the cosine hyperbolic. Okay, so this is how the B looks like. Okay, and for the current, so the current is actually given by so similarly in the y direction, so it has a y dependence. So between minus a and plus a, so the current is actually an odd function. Okay, so outside there is no current because this is vacuum. So the current has a sine hyperbolic. So let me try to draw a sine hyperbolic. Okay, it is kind of a sine hyperbolic, but yeah, I mean, imagine that it is a pure sine hyperbolic. Okay, so this is the current J, and this is the magnetic field. Okay, and what about the directions? So again, let me just draw another picture. So I have a slab. Okay, so this is my y direction, and this is my x direction, and this is my z direction. Okay, so inside the magnetic field is also it is being generated in the z direction, right? And for the x, so the current, you see that so at x is equal to a, at y is equal to minus a, the current has a negative direction, right? So that means on the left hand side, the current will be on this negative direction. So that means, so current will be like this, and as you go inside, it will decrease, and you see that as you change your y to be plus a, the current becomes positive, right? So it should be in the positive x direction, so it should be pointing somewhere here. So then what happens is that, so on the other edge, this current is maximum on the edge, and then it decays with some sine hyperbolic form and 0, and then it reaches 0 exactly. And so you see that, so the current is actually moving in the opposite direction. Okay, so it's kind of interesting thing. So yeah, so this is how the this profile of magnetic field of current looks like. But now here we see that there are actually two length scale which we can vary. So for example, so what are the two length scales? So the one length scale is, so the slab's width is given by 2a, right? So it is okay. Again, my screen has frozen. Okay, so let me again rejoin. All right. Okay, so yeah, so I was telling you that, so there are two length scale. One is the slab's width. So slab's width is given by 2a, right? And the another length scale we have is the London's penetration depth, or so London's penetration length, something like that. So which is given by lambda L. Okay, so we can assume two scenarios. So the one scenario will be, so when the lambda L is much larger than the length scale A, and the another one is when lambda L is much smaller than A. Okay, so let me draw pictures for all of these things. So we know all of these results. So what we need to do is, now we just need to plot them for different values of A and lambda, right? So that the physical picture becomes fully clear. Okay, so I'll again draw something like this. So this is y direction, and I'll be plotting the magnetic field and also the current, the magnitude of those at least. Copy. Okay, so let's say this is my magnetic field and this is my magnitude of the current. Okay, so as you have seen, so let's say that my lambda L penetration length is much larger than A. So then what will happen is, so before my signal is fully exponentially decayed, it will start growing again, because it has to join the boundary condition, right? So that means, so this is my external field, and then it will decrease, it will obey the cosine hyperbolic, and then it will again rise up and it will join the external magnetic field, right? So this is what is expected, because it cannot fully decay inside this slab, because slab is not that large, not that huge. Okay, on the other hand, the sigma is like, so let's say this is my A, this is plus and this is minus A. So if you carry, so this probably this is your lambda L. Okay, but the slab is finished before going to that distance, so then it will again increase. Okay, so similarly the current will also be something like that. So current will current will be something like that. Okay, it is not a very, so something like that. So it is a sine hyperbolic, but the current is actually non-zero up to a very bulk part of this slab. Okay, it is like non-zero up to that point, because the magnetic field is all there. Okay, so this is one limit, when this penetration depth is much larger than the slab's slab's thickness. So the other limit is the opposite. So let me bring this here. So okay, so let me draw this again. So this is for the other case. So when lambda L is much smaller than A, so you can probably already see what will be happening. So let me just draw this quickly. Okay, so this is the magnetic field B, and similarly I'll have the current. So here you see that, so there is some external magnetic field which is constant, and then it will decay very fast. Okay, and then it will also rise here. So the lambda L is actually really much smaller, so it decays very fast inside the bulk. Okay, so you can actually really see that around those parts the magnetic field actually is zero. Okay, so that means it has kind of a very good screening to external magnetic field. So on the other hand, the current will be sharper, so it will become like this, it will become zero very fast, and then also it will grow. Okay, so current becomes really zero as you go inside the bulk, right? So this is like two two opposite limits. I mean, just to give you a clearer picture of what is really happening. So yeah, this is interesting, and I mean, this is not something that you do in electrodynamics and in many superconductivity courses, but yeah, this is really interesting. So there is one last problem that I'd like to show you. Yeah. Okay. Okay, so now I have infinite cylinder. Okay, so it is infinite in z direction. So I have a external magnetic field, okay, in this z direction. Okay, and what I am asking is now again, so do the same business, calculate the magnetic field and also calculate the current density. Okay, so that is all I am asking. So here also our main starting point is the London's equation. So this is an infinite cylinder. And we have this B applied is a constant, is in z direction, and it has this oscillatory part. Okay, so now, so this the thing that we are trying to do is we want to solve this London's equation given by this inside the superconductor, right? So now we see that this system has a cylindrical symmetry. So the natural coordinate system to use is a cylindrical coordinate, right? And so in that the calculation will exploit the symmetry and calculation will become a lot easier. Okay, so and before that, let us actually try to see that what should be the solution be like, right? So we're looking for a solution which is in the z direction, because the applied magnetic field is in the z direction. Okay, and because the magnetic field doesn't have any azimuthal like phase e to the power I phi, something like that. So we'll say that this is actually this has a circular symmetry. Okay, so then at any azimuthal angle you look at the current, it should be the same. So it should not depend on that phi. Okay, that azimuthal angle. So azimuthal angle is just this phi. Okay, so the solution should not depend on the phi. Okay, so but it should depend on only the radius, because it will get screened as it goes towards the axis of the cylinder, right? So the solution by this physical argument is we are looking for is b of rho. So this rho is the distance from the center. Okay, so it is just I am using the normal I mean the normal symbols of spherical of this cylindrical coordinate. So that's why this rho is the distance from the center of the cylinder, right? So yeah, and yeah, and the this phase part should be same. Okay, so what will happen now is, so now so we can write this gradient operator in this cylindrical coordinate. So because we have only this r dependent rho dependent function, so the expression is not that complicated for our case. So the Laplacian is given by 1 by rho del rho, and then rho del b function of rho and del rho, right? So there is no other term, because other terms will be something proportional to del phi and del z. Okay, but our function, the solution that we are trying to find, is that doesn't depend on phi or z. Okay, okay, so now what we have is so let's put everything together, and we will have 1 by rho del rho del b rho and del rho, and minus 1 by lambda L square. Or b rho, yeah, this is 0. Okay, so now we'll try to solve for the b rho. Okay, so now let's try to simplify this furthermore. So then this is 1 by rho, and so times rho del 2b del rho 2 and plus 1 by rho del b rho and del rho minus b of rho lambda L square is equal to 0. Okay, so in the first term this two things cancel each other, so I'll just remove those. So apparently this looks like some complicated expression. Okay, but let me give you some hint that this is actually this is what we study. I mean, something very much close to this we really study in mathematical methods. Okay, so this is some sort of special, the solution is some sort of special function. So I'll first start with a hint. Okay, so so let me write this expression z square or let me d2y dz2 dy dz. Okay, and yeah, minus z square plus n square y. So this is actually, this is something that is called the Bessel's equation. So okay, not this, okay, plus z square minus n square, yeah. So this is called the Bessel equation. So we see that there is some kind of similarity with this. Okay, and the solutions are actually Bessel function, so which is written by JNZ. Okay, so now I mean normally we have seen that for a Cartesian coordinate problem we have only exponent e to the power minus x, e to the power x, or sine hyperbolic or cosine hyperbolic, but this kind of symmetry, this kind of circular symmetry, whenever you will have, you will see that somehow this Bessel's function will start appearing. Okay, so like these Bessel's functions are what these sines and sine hyperbolic, cosine hyperbolics are in one dimension. Okay, or something like that. Okay, so but our expression is not quite like that, right? So so this is called a Bessel's equation, and so there is something called a modified Bessel function, so for which we have just a sign difference. So let me write that. So this is called a modified Bessel function. So for which the solutions are written as some with some symbol I and Z. I mean, so this is just something that you can get out of any handbook of these formulas. Okay, so this is something that you don't have to remember, but so this is, I mean, so some hint you can get from, again, just because of this circular symmetry or this cylindrical symmetry, the solution, the Bessel function should appear in the solution. Okay, so with that, so with these things, so you will see that if we plug in n is equal to 0, okay, so let's try to see where do you go with this. So in the last modified Bessel function, just put n is equal to 0. Okay, so then what will happen is, so we'll have z square d2y dz square plus z dy dz minus z square y is equal to 0, right? So now let's divide the full thing with z square. So what we will get is, so we'll get 1 by z here, and then this z square will be gone, right? So this the solution of this equation is the modified Bessel function of 0th order, and inside is just the y, or not the y, the z. Okay, so and you see that our expression apart from some factors, some constant factors, it looks exactly like this, right? So these two equations look exactly like the same, right? So I know you'll just say that okay, this is a solution of a special, this is just a special function which is just the modified Bessel function. Okay, so with that, so this is not very important anyway. So the Bessel function you can find anywhere in any kind of handbooks of formulas. Okay, so I'll directly write the solution with this motivation. So the solution is actually given in terms of some constant times this Bessel function of rho. Okay, so the task at hand is to find the constant itself. Okay, so to find that constant we will take help of the boundary condition, right? So boundary condition is at distance r, so just outside the cylinder, so this is given by some constant, right? So this is our boundary condition, so we'll plug that in. Okay, so I have actually missed something, so it is rho by lambda L. Yeah, so this is the full solution. So outside this cylinder, just outside the cylinder, so the magnetic field is B naught, and then I have this I naught R by lambda L. Okay, so that means the C will be given by B naught by I naught R by lambda L. Okay, so the full solution, how does the full solution look like? So B R and function of t is given by B naught times the modified Bessel function R by lambda L. Okay, not R, this is rho by lambda L divided by I0 R by lambda L, right? So you will see if you plot this function, so the function actually looks kind of simple. So let's say this is my rho direction, okay, and I am plotting this magnetic field. Okay, so it actually is 0 exactly at the center. Okay, and then it grows and grows, and at r, at the radius of this cylinder, it becomes B naught. Okay, and then it continues to be that. Okay, so this is how the solution looks like. Okay, so yeah, and yeah, so the other thing, okay, so and this is in the z direction, and also the oscillatory part, real part of e to the power I omega t. Okay, so now the one important thing is, okay, I know the magnetic field. Now what is the current? Okay, so for the current we'll just again calculate in the similar way the curl of B. So current is given by curl of B. Okay, so here we'll be again using curl in the cylindrical basis, right? So the curl in cylindrical basis is defined like this. So something like okay, so let me first quickly write this definition of some vector field, okay, which is given by some 1 by rho hat, rho phi cap, z cap, del rho, del phi, del z, and then a rho, a phi, and a z. Okay, so for our case a rho and a phi are 0, so we have to do some less amount of multiplications and all. So 0 0, and for this part we have some I0 function rho by lambda L. Okay, and there are some other things. Okay, so which okay, so let me write it properly. So some other things are B0 1 by I0 R lambda L. Okay, so here also we see that so there will be just this okay, so let me, yeah, so this is interesting. So for the rho cap term this is 0. Okay, for the phi cap term what will happen is, for the phi cap, so this del z will act on 0 and then del rho will act on this part. Okay, so that means I have minus del rho acting on I0 rho by lambda L. Okay, all of the other things are 0. Okay, and so okay, so let me write the other parts also. 1 by B0 mu 0 I0. Okay, B0 is on the top, B0 R by lambda L. Okay, so you see that the direction is in the phi cap, so we will have some azimuthal kind of current, right? So cap, and so there is some another identity of this special function, so which is like if you have some I naught, some rho by lambda L, so that the derivative gives you I1 rho by lambda L and 1 by lambda L. Okay, so the result will be B naught mu naught, so I1, so there is minus, so I'll have a minus I1 rho by lambda L. Okay, and then on the top I'll have I naught R by lambda L. Okay, so this is the full current. Okay, so now let's visualize all of this thing together. So now if I have this cylinder which is infinite in this z direction, and I have only this external I have this applied field outside, so what will happen is so as the field will enter the cylinder, so it will actually decrease, so it's not in exponential fashion but in a Bessel function way, but it will decay, right, something like that. So this is how the magnetic field is, and for the current we will have something like this. So let's say this is my cylinder, and so this is my phi direction, right? So this is the phi direction. So so in my solution I see that the current will actually flow in the minus phi direction. Okay, so so let me just try to draw it. So current will flow in this minus phi direction. Okay, so you can assume that okay, the current will flow in the clockwise way. Okay, and as you will go inside the bulk, so you will see that the magnitude of the current will actually decrease. Okay, and it will become very small as it will go inside. Okay, so the full picture is we have some applied magnetic field in z direction. Okay, and there is some current generated in the minus phi direction. Okay, so you can actually try to make sense of this result in terms of some thumb rule. So if the magnetic field is in the z direction inside the cylinder, so that means that the current will be generated in the minus phi direction. Okay, so some sort of thumb rule probably will tell you that this direction is something that makes sense. Yeah, okay, yeah, so we have used a lot of not a lot of, some special function in here, but so whenever you will be given this kind of question, you will be given with a table for the appropriate formulas, I hope. So, and anyway, this is interesting to look at things like how does this electromagnetism work in superconductors. Okay, which is like a very counterintuitive kind of way, right, than the normal conductors and normal things what we learned in the electrodynamics classes. Okay, so yeah, I have only this much amount to cover today. So please, if you have any question, feel free to ask, I guess. All right, so if you have no other question, then we'll close this session for today, and we'll meet again next week. Okay, so bye then, and have a nice week. Okay.